I welcome you all to lecture number 29 of this course. Now, before I start with today's topic, I have one experience to share with you, and there will be some announcement. Now, a few days ago, 2-3 days ago, I was reviewing one international journal paper, and the paper was on multi-layered feed-forward neural network. So I was examining that manuscript, and suddenly I could find that there is one fundamental mistake in that particular the paper on multi-layered feed-forward network. So what is that mistake? Now the reason why I am sharing this particular experience, you should not make that particular mistake. Being one of my students, please do not make this mistake. The mistake was as follows. Now the authors from abroad, so they were uh, writing that particular paper on application of multi-layered feed-forward network. Now to decide the topology of that particular neural network, they carried out one parametric study, and while carrying out that parametric study, by mistake, they varied the number of hidden neurons starting from 1 to 5. Okay. Now, the minimum number of hidden neuron for a multi-layered feed forward has to be equal to 2, not equals to 1. There is a reason. The reason is, if you see the earlier paper, the fundamental papers on multi-layered feed forward network, a few years ago, there are some studies what should be the minimum number of hidden neurons in a multi-layered feed-forward network. And there it was proved that the minimum number of hidden neurons to be placed is equal to 2. The reason is, if you want to capture the generalization capability of the process by the neural network, or if you want to capture the dynamics of the process to be maintained, a model, so the minimum number of hidden neurons should be kept equal to 2. So I can vary from 2 to say might be 20 or whatever may be, but the minimum number is 2, not 1. Okay. Now I'm mentioning now because most probably I forgot to mention whenever I discuss the principle of multi-layered feed-forward network. Okay. So I have given that particular comment to the paper, to the authors. That has to be modified. Otherwise, it could not be considered for publication. Okay. And I thought I also forgot to mention in this particular class to you. Okay. So please remember this. The minimum number of neurons to be placed on the hidden layer for a multi-layered feed-forward network is equal to 2. Okay, please do not forget this. I hope I am clear. Okay. Now next is your announcement regarding the third test. Okay. Now for the UG course, that is the soft computing course, your third test will be held on 11th November. Okay, today is 4th. So after 7 days, so 11th November is Wednesday, and we are going to start at 12. Okay. Now, following the same procedure, I'll be taking your third test. Just before 12, I'll be sending the question paper, okay, to the students of soft computing, but not knowledge-based system. So this is only for the students of soft computing, that is the UG course. Okay, and there will be usual class for the knowledge-based system on 11th. After I start the exam, I'll be taking the class for the knowledge-based system students. Okay. Now, so on 11th, we are going to start the third test for soft computing, and we are going to start at 12 p.m. for 1 hour as usual. Now, regarding the third test of knowledge-based systems in engineering, that is the PG course, that will be held on 13th November, 1-3. 13th November is Friday. Okay, and we are going to start at 9 a.m. Once again, the test will be for a maximum of 1 hour. Okay, so let me repeat. The third test for the knowledge-based system will be held on 13th November, that is Saturday, and we are going to start at 9 a.m. Okay, so I think there is no confusion regarding the test. There is another announcement. There will be one more assignment, very simple assignment. And here, it is not the numerical example. This is some sort of conceptual question. Okay. Based on the things, whatever I have discussed in the class and whatever you could learn, based on that, I'll be designing your assignment 5. Very simple. And assignment will not be taking more than 3 days to solve. Okay, that will complete the course. Okay, that will complete the course, and I'll be submitting your grades by 21st. I hope I am clear. Okay, now let me start with today's topic, a very interesting topic that is called the neurophagy system. Like how to combine the neural network with fuzzy logic to develop the neurophagy system to solve some real world problem in a very efficient way. So that I'm going to discuss. Now, if you see the literature, the neurophagy system, okay, that has been designed and developed both for the Mamdani approach as well as for the Takagi and Sugene's approach, which we have already discussed. Okay. Now, before I go for that, the neurophagy system in details, let me share one knowledge that is regarding the combined techniques of neural networks and fuzzy logic. Now remember, just like our genetic algorithm and fuzzy logic, that combined tools, the combined techniques or tools of neural network and fuzzy logic have been designed and developed in two different ways. Okay. Now, in the first approach, that is called the neurophagy system, a fuzzy logic controller or a fuzzy reasoning tool is represented using the structure of a neural network. Okay, and it has been trained using either the backpropagation algorithm or say a genetic algorithm. Okay, let me repeat. So this neurophagy system, in short, this is known as NFS. Okay, it's basically a fuzzy logic controller or fuzzy reasoning tool. But to represent that fuzzy reasoning tool or fuzzy logic controller, we take the help of the structure of a neural network. I'll show you. Look-wise, it will seem that it is just like a neural network, but basically that is a fuzzy reasoning tool. Let me repeat. Neurophagy system is basically a fuzzy reasoning tool expressed using the structure of neural network. Now my question is, why do we use the structure of neural network to represent the fuzzy reasoning tool? The purpose is very simple. If I can represent the fuzzy reasoning tool or fuzzy logic controller using the structure of a neural network, very easily I'll be able to give the required training using the backpropagation algorithm or by using any other nature inspired optimization tool like genetic algorithm and others. Okay, so I'll be discussing in details this particular the neurophagy system, and as I told, There is another combined technique using the fuzzy logic and neural network that is called the fuzzy neural network. In short, that is known as FNN. Now here, what is the purpose? The purpose is just the reverse. Okay, here the neuron of a neural network has been designed using the concept of fuzzy set theory. Okay, so inside that particular neuron, there will be fuzzy set. There could be fuzziness in the weights of that particular neural network. There could be fuzziness in the inputs of the network, and all such things have been modeled. The fuzziness of all such things have been modeled using the concept of fuzzy set theory. And that is very popularly known as fuzzy neural network, FNN. Okay, a few years ago, I had one MTech student from computer science department here. Okay, I was a joint guide. Okay, and we developed one fuzzy neural network to solve some problems related to robot motion planning. Okay, but that particular paper we did not publish because that student also left. So we could not publish that particular paper. Okay, that particular manuscript is still unpublished, and now I'll not be able to find the trace of that particular manuscript also. Okay, now the way we developed that fuzzy neural network, what we did, we consider three sub approaches. In sub approach 1, we consider the real inputs but fuzzy weights of the network. In second sub approach, we consider fuzzy inputs but real connecting weights. And in the third sub approach, we used fuzzy inputs and fuzzy weights. Okay. Now, after doing all such things, we could realize one weakness of this particular approach. The weakness is as follows. Now, this fuzzy neural network may not be very suitable technique for online implementation. Okay, and that is why actually this particular approach of fuzzy neural network could not reach much popularity the way it has been reached by your neuropuzzy system, that is NFS. Neuropuzzy system is the most popular one, and so far as I know, if you see all the soft computing approaches, the maximum number of paper you will be getting on the neuropuzzy system, that is NFS. Okay, and I'm just going to discuss the way we could develop this particular NFS to solve a variety of problems. Okay, now let me try to concentrate on the neuropuzzy system based on the Mamdani approach. Now this particular the figure, that is actually the figure related to your neuropuzzy system based on Mamdani approach. I think this figure has been made little bit smaller. It may not be easy for you to read, but let me continue this. Supposing that I have got a system having two inputs, that is I1 and I2, and I've got only one output, that is O. So our aim is to model this input output relationship. Okay, if you remember the problem of robot motion planning, okay, where we implemented and we did the real experiment also. So the first input could be the distance between the robot, the planning robot, and the most critical obstacle. And the second input could be the relative angle of that, the most critical obstacle with respect to the planning robot, and output could be the angle of deviation. Okay. Now here, as I told, that this is basically a fuzzy reasoning tool working based on the principle of Mamdani approach, which all of you know. Okay, but look-wise, you see, it is just like a neural network. But basically, this is the fuzzy reasoning tool based on Mamdani approach. Let us see how to design. So we pass the two inputs I1 and I2 through this particular the input layer. Okay, and on the input layer we use linear transfer function. So output is nothing but the input. So I'll be getting this particular the output. Now here you can see I have mentioned that is your low, medium and a high. That is L, W, M and H. Now this low, medium and high are the linguistic terms used to represent the first input. Similarly, your very near, near, far and very far. So these four linguistic terms are used to represent the second input. That means we'll have to consider some membership function distribution. In fact, I consider the triangular membership function distribution for simplicity. We can also consider some other nonlinear membership function distribution. So this is the membership function distribution for the first input, low, medium and high. The membership function distribution for the second input, very near, near, far and very far. Membership function distribution for the output, that is your slow, fast and very fast. Okay, so now we can remember this is nothing but the Mamdani approach of fuzzy reasoning tool, which I am going to discuss. The moment we pass your this particular input to the second layer, so I'll be getting the output, and this output is nothing but the membership function distribution corresponding to this input. Okay, how to determine, all of you know. So I can find out the output of the second layer, and second layer is called the fuzzification layer. All of you know the meaning of fuzzification. Corresponding to the real input, so I'll be getting the membership function distribution values here. Okay, so I'll be getting the output of the second layer. Now here, for the first input, there are three linguistic terms. Second input, there are four linguistic terms. So 3 multiplied by 4. So there are 12 rules on layer 3. And the layer 3 is going to perform the AND operation. All of you know the AND operation. That means we are trying to find out the minimum of the two membership function values. Okay, as output. So on the layer 3, depending on the fired rule, so I'll be getting the output. And once you have got this particular output, now we go for the fuzzy inference, that is your layer 4. And all of you know the meaning of fuzzy inference. Through the fuzzy inference, we'll try to identify the fired rules corresponding to the set of input. And once we are able to identify the fired rules corresponding to the set of input, so we can find out actually your the output, and we just sum them up here, and that is nothing but is your we can consider the combined effect of all the fired rules. Then we'll have to go for defuzzification, because here as input for the fifth layer, we got actually the fuzzified output, and that particular fuzzified output could not be used directly as the output. So we'll have to go for defuzzification in layer 5. And consequently, I'll be getting the crisp output corresponding to the set of input. I hope you have understood that this is nothing but the Mamdani approach of fuzzy reasoning tool. Okay. And once you've got this particular output, so what you can do is you can go for either back propagation algorithm to update these connecting weights, okay, and to a large number of iterations using the back propagation algorithm or genetic algorithm, you will be able to evolve a particular neurofuzzy system. And once it is trained, if you pass the test cases, it will be able to make the prediction of the output very accurately. Okay, so this is the way actually the neurophagy system based on Mamdani approach works. Okay, all of you know the Mamdani approach, so it is not a problem. Okay, now I'm going to tell you the way we could design. So this is the membership function distribution for the two inputs and one output. And this is the possible rules. Okay, you can say these are the manually constructed rules. You can say there are three linguistic terms for I1, four linguistic terms for I2. So there is a maximum of 3 multiplied by 4, 12 rules in the rule base. And depending on the set of inputs at a time, how many rules are going to be fired? For the first input I1, there could be two possibilities if I consider this type of membership function distribution. Similarly, for I2, there will be two other possibilities. So 2 multiplied by 2. So out of these 12 rules, for a set of inputs, a maximum of 4 rules will be getting fired. Okay. Now, the thing I'm going to discuss, and this schematic view shows the input and output of each of these particular layer, which I've already discussed. Let me repeat a little bit. This is layer 1, so the linear transfer function. I'm passing the input, I'll be getting the output. That output will be multiplied by this particular VJK, but here this VJK is going to indicate something else. What is that? That is nothing but the half base width of the isosceles triangle, or the base width of the right angle triangle used to represent the membership function distribution. I'll be discussing the next slide. Okay, this is not like ordinary connecting weight, which we generally multiply with the output. There is a difference. Okay. Now this is the input, 2ik is the input for the second layer, and I'll be getting 2ok as the output. This is the logical AND operation we try to implement in layer 3. I'll be getting some output, okay, and in layer 4 there will be fuzzy inference. That means the fired rules will be identified, their fuzzified output will be identified, and those fuzzified output will be combined as input of the fifth layer, and as output you'll be getting your the crisp output corresponding to the set of inputs. Okay. Now here, please try to understand. We have done something for simplicity of that particular the network. You just read it out, then I'll tell. V1 average is nothing but V11 plus V12 plus V13 divided by 3. So I have got the average value. And after that, I'm assigning V11 is equals to V12, that is equals to V13, that is equals to V1 comma average. Now my question is, why did I do like this? As I told, this we did just to make it simple. Let me go back to the network, you'll understand very easily. Okay. Now here, the connecting weights between the layer 1 and layer 2. Okay. So this is nothing but V11, this is V12, this is V13. We sum them up, find out the average, and after that we put equal to V11 equals to that average value, V12 is equals to that average value, and V13 is equals to that average value. What does it mean? It means that I'm considering the symmetrical membership function distribution for I1. Now, if I want to actually implement asymmetric membership function distribution, then I should not assume that V11 equals to V12, that is equals to V13, and that is equals to V average. But here we consider the symmetrical membership function distribution for the triangular membership function distribution of I1. That is why the way we implemented, we assume this to make it simpler. Okay. The similar type of thing we did for I2. So once again, we try to find out V24, V25, V26, V27. We add them up, find out the average, and individually, that is V24, 25, 26, and 27, we keep it equal to the V2 average. Once again, we did it just to consider the symmetrical membership function distribution for I2. And once again, for this membership function distribution, we follow the same principle. Okay. And you can see that. So the same thing we do to find out V2 average, then comes your W average is nothing but W11 plus W21 plus W31 divided by 3. After that, we assign W11 equals to W21 equals to W31, that is equals to W average. Okay, so this is the way actually we could consider the symmetrical membership function distribution. Now, whatever I discussed, the same thing I have written it here. You can have a look. Layer 1, linear transfer function, output equals to input. Layer 2 is the fuzzification. Okay, and how to carry out that fuzzification, how to determine the membership function distribution, all of you know. Okay, I'm not going to spend much time on this. All of you know how to find out the membership function distribution. Layer 3 performs a logical AND operation. All of you know this is the mean operator. Layer 4 carries out the task of fuzzy inference, and layer 5 is the defuzzification. Now, to design the transfer function of layer 5, so we'll have to take the help of some method of defuzzification. Say center of sums method, centroid method, mean of maxima method, and so on. Okay. So here we use center of sums method, and all of you know, according to center of sums method, how to find out that particular the crisp output. Okay. Now, how to provide the training to the neurophagy system? So generally we use batch mode of training to train this type of neurophagy system. As I told, we can use either the back propagation algorithm, or we can use some nature inspired optimization tool like say genetic algorithm and others, okay, for the purpose of training. And once it is trained, now we can pass the test example unknown cases, okay, so that you can find out the output for a set of input. Now remember one thing, as I told, just like the other algorithms, okay, so before you could develop, before I could write in my textbook on soft computing, before I could publish this particular paper, see, the life was not so smooth. I can share that experience. When I was trying to develop this, okay, I started, I remember, uh, towards the middle or the end of 2002. Before I joined IIT Kharagpur as a faculty, I started working on it. Okay, then uh, I joined in 2003. Okay, and I could make some progress, but life was not so smooth. So I should not claim that in one trial I could make it working condition. There are a lot of success, failure, trials and others, lot of modification, lot of thinking. Ultimately, it could work. Okay. Now, just to model that experience I gained, immediately I designed some numerical example so that I can explain it to my students. Okay. Now the same numerical example I'm going to discuss it here, and most probably I do not remember, might be the same example I have taken in my own textbook also on soft computing. I hope so. Now let me give the statement of this particular the numerical example. Figure 4, sorry, figure shows No, I think this numerical example, I do not remember. Might be it is there in the exercise of my textbook or in the solved example. Anyone. Now, this numerical example is such, it shows the schematic view of a neurophagy system that I'm going to show in the next slide, in which an FLC, that is the Mamdani approach, has been represented using the structure of a neural network. There are two inputs, I1 and I2, and one output, that is O of the controller. The NN consists of 5 layers. The function of each layer is indicated in the figure, which I'm going to show you. The input I1 has been expressed using 3 linguistic terms, that is near, far, very far. Similarly, 3 other linguistic terms, namely small, medium, large, have been utilized to represent the second input, that is I2. Moreover, the output O has been represented using 3 linguistic terms such as low, high, and very high. Okay, now I'm just going to show you that particular this is actually the figure corresponding to that numerical example. Once again, I'm very sorry. I hope you'll face a little bit of to read out this particular the figure. It is too small. There are two inputs, I1 and I2. To represent I1, there are 3 linguistic terms, near, far, and very far. And to represent I2, small, medium, and large. So 3 multiplied by 3, there are 9 such rules on layer 3. And this is the fuzzy inference layer. This is the fuzzy deiffication. And then you'll be getting the crisp output. Okay. Now, the remaining part of the statement, the membership function distribution of the inputs and output are assumed to be triangular in nature. You can also consider Gaussian or any other nonlinear distribution. For the first input I1, the base width of near, very far, and half base width of far triangle are kept equal to V11, V13, and V12 respectively. Similarly, V24, V26, and V25 represent the base width of small, large, and half base width of medium triangles respectively. Moreover, W11, W31, and W21 indicate the base width of the triangles representing low and very high outputs and half base width of high triangle respectively. The starting values of I1, I2, and O are assumed to be equal to 1.0, 10.0, and 5.0 respectively. Determine the deviation in prediction for a case given below, that is I1 is 1.6, I2 is 18.0, and the target output is 9.0. It is very simple and already I have discussed. So you'll find that very easily you'll be able to solve it. Let us assume statement is not yet finished. V11 equals to V12 equals to V13 for symmetricity of that membership function distribution. Similarly, V24 equals to V25 equals to V26. Then comes W11 equals to W21 equals to W31 for simplicity. And some numerical values we are assigning, like V11 equals to V12 equals to V13 is equals to 0.3 in the normalized scale. Then V24, V25, 26 equals to 0.6. W11, W21, W is equals to 0.4. Okay, let us suppose that B1, B2, B3 of figure represent the real values corresponding to the normalized weight. So these are all normalized weight. It corresponding real values are to be represented by B1, B2, and B3 in the figure. Okay, you can see in the figure there are some B1, B2, and B3. I think it is there next to that. Okay, and these are the ranges for B1, B2, and B3. Yes, this is B1, this is B2, and this is your B3. Okay, so these are the ranges for B1, B2, and B3. So you have to find out the real values for this B1, B2, and B3 lying within their respective ranges, and by using this particular your normalized weight. Okay. Now the B values are assumed to lie within the following ranges. Use center of sums method for defuzzification. Let us see how to get the output corresponding to the two inputs I1 and I2. So these are the initial membership function distribution for I1, I2, and your O, that is the output. B1 indicates the base width of the right angle triangle and half base width of this isosceles triangle. Similarly, B2 is used to represent I2 and B3 is used to represent the output. Okay. Now here, how to find out the real values for B1, B2, and B3 corresponding to its respective range and the normalized value of the connecting weight. Now x is nothing but the real value of x is nothing but n multiplied by n max minus n min plus n min. Sorry, x min. X min is what? That is the minimum value of x. X maximum minus x minimum is the range for x, that is multiplied by the normalized value n, which will lie between 0 and 1. If you put n equals to 0, x will become x min. If you put n equals to 1, x will become x max. So this is the way this particular relationship has been designed. It is very simple. So by actually inserting the numerical values, you will be getting the real values for this B1, B2, and B3. So B1 is found to be equal to 0.8, B2 is found to be equal to 11.0, and B3 is found to be equal to 4.4. So these are the real values for B1, B2, and B3. Okay. And once you've got the real values for this B1, B2, and B3, you will be able to modify the membership function distribution for this I1, I2, and O. And these are nothing but the membership function distribution for I1, I2, and O. Okay. So you can see that the base width for the right angle triangle and the half base width for this isosceles triangle, so those are now modified. Okay. So this was the rule base, and as I told, out of these 12 rules, at a time a maximum of 4 will be fired. Okay. And this is layer 1. So output is nothing but input, and we have got the linear transfer function. Okay. And layer 2, we try to find out the membership function value corresponding to the set of inputs. Okay. So this is nothing but the fuzzification module. Okay. So you will be getting all such membership function value corresponding to near, corresponding to far. Then membership function value corresponding to small, corresponding to your medium. Now these are the 4 fired rules out of 12. So these rules are going to be fired. The rules are as follows. If I1 is near and I2 is small, then the output is something which is there in the table of the rule base. Next is if I1 is near and I2 is medium, then output is something. The third fired rule, if I1 is far and I2 is small, then the output is something which is already there in the table. If fourth rule, if I1 is far and I2 is medium, then the output is something which is there in the rule base table. Okay. Now, so I'll be getting the inputs of the third layer, that is nothing but two membership function values, and here we carry out the AND operation. So we'll compare these two, find out the minimum as the output, compare these to find out minimum, compare these to find out minimum, compare these to find out the minimum. So this is nothing but the output of your layer 3. And once you've got this output of the layer 3, now in layer 4, actually what you can do is, so we try to combine all such your the output, and you'll be getting the fuzzified output as the output of layer 4. So you can see that. So these are actually the fuzzified output for the first fired rule, second fired rule, third fired rule, and the fourth fired rule. You can see that shaded portion is the output of the individual fired rule. Then we combine, and if we combine, you'll be getting the combined fuzzified output, which is nothing but your this shaded area. And we'll have to go for defuzzification in layer 5. And as I told, we use center of sums method to find out what could be the output. And once you've got this particular output, now this output will be compared to the target output, and we can find out the deviation. Are you getting my point? Now, if I'm using the genetic neurophagy system, that means your neurophagy system trained using genetic algorithm. So in the population of GA, there will be a number of GA string. Say you concentrate on the first GA string, then you pass all the training scenarios one after another. So I showed you how to pass one training scenario. By following the similar method, you pass the second training scenario, the third training scenario, and so on. After passing all the training scenarios, you find out the average of the deviation. Of course, before that, you'll have to consider the mod value, that is the positive value corresponding to the deviation. Now, that particular average deviation will be the fitness for the first GA string. Then you concentrate on the second GA string, find out the fitness. For the whole population, you find out the fitness. Then GA will use its own operator, reproduction, crossover, and mutation. And for a large number of iterations, it will try to find out that particular neural network or that particular set of neural networks which will correspond to the minimum error in prediction. So this is the way you can combine the genetic algorithm also along with the neurophagy system, neurophagy system to develop the genetic neurophagy system. Okay. So I hope this particular, the method is clear to all of you. But if you have any doubt regarding today's class or yesterday's class on genetic neural system, we can spend some time to clear your doubts if you have. Okay. And today I'm not going to start with a new topic that I'll be doing tomorrow. So tomorrow we are going to meet at 11. Okay. To start with a new topic. But before that, I have some time. So if you have any doubt, I'll try my level best to clear your doubts. So you can ask me if you have any doubt. Please.
Hello, sir.
Yes.
Sir, in slide 23.
Slide 23. Tell me the topic.
Yes, sir. It was the yes, sir. That one.
This one.
No, sir. It was the network, sir, the fuzzy network.
Okay. Okay, let me concentrate on this example. Same thing. Tell me.
Yes, sir.
Hmm.
In this, between layer 2 and layer 3,
Hmm.
and layer 3 and layer 4,
Hmm.
there are no connecting weights.
No connecting words. No
Yes, sir.
connecting words. Actually,
But
while designing this neurophagy system, always you'll have to think about the working principle of Mamdani approach. Okay, this is not the conventional multi-layered feed-forward network. Always on the background, you'll have to think about your Mamdani approach of fuzzy reasoning tool. Accordingly, you'll have to design. Okay, initially I had a tough time. Okay, to come up to this particular design, and after that we could implement and tested it, and it worked very successfully. Here, as if the connecting weight is one. Okay, and practically whenever we wrote the program, so we consider as if it is one. So whatever output we are getting, the whole amount is coming as input to the next layer, something like that. Okay, but this AND operation, what should be the transfer function? The transfer function is the comparison of your two mu values and find out the minimum mu value as the output of this particular layer. It is not the conventional transfer function of the multi-layered feed-forward network. Okay, so keeping in mind what is happening in that particular your AND operation layer, you'll have to design that particular transfer function. As if the way the computer program was written, so two mu values will come, one from I1, another from I2. We compare, find out the minimum. That will be the output of that particular the rule. Okay. This is the way actually
yes,
your
yes, sir.
this particular thing was designed. As I told, it was not so smooth. I had a very tough time to design and then to make it in working condition. Okay.
Yes, sir. So it was done to keep the physicality of the system.
Yeah, yeah. Now you'll have to not the physical of the system. You'll have to see about the working principle. You see, it is loop-wise a neural network, but on the background, the fuzzy reasoning tool of Mamdani approach is implemented. Okay.
Yes, sir. Okay, thank you, sir.
Okay. Any other doubt? Any other doubt?
Can you hear me, sir?
Yeah, please.
Yeah. It's just a follow-up, but I consider it as trivial. So can you call this as fuzzy-inspired neural network?
Just a minute. Fuzzy inspired neural network. Actually, if you say fuzzy inspired neural network, then you'll have to see which one is primary, which one is secondary. Okay.
Yep.
The primary is fuzzy reasoning tool. Okay.
Okay.
Secondary is actually NN structure. Okay.
Okay.
If you say it is fuzzy inspired neural network, it is wrong. Okay. The reverse could be true. It is neural network inspired fuzzy reasoning tool.
Okay.
Am I clear?
Yes, yes. I mean,
Okay.
I just asked you because this has the structure of neural network.
Yes, yes.
That's the only reason.
But the primary thing is fuzzy reasoning tool. Secondary is the
Okay.
neural network structure. That you have to understand. The
Okay.
reverse would be more appropriate. Okay.
Okay. Thank you, sir.
Any other any other doubt?
Sir, then will there be any bias values or there won't be any bias values in there?
We did not use any bias value. In our implementation, we did not use any bias value. But if you want to add some small value, you can add. Okay, like 0.01 or 0.005, something else. But we did not use any bias value. Okay, you can see our paper published in so many journals, particularly in fuzzy sets and systems. Okay, a very like your well cited paper. where the real experiment was also done on robot motion planning using this particular technique. Okay.
Okay, sir. Thank you, sir.
Any other doubt? Okay, so there is no doubt. So let me stop here today, and we are going to meet once again tomorrow. That is your 5th at 11 a.m. Okay, and we are going to start with a new neurophagy system. Okay, in fact, that is actually the most famous. That is known as ANFIS. If you just give the search in Google, okay, ANFIS, you'll be getting a very large number of papers. In fact, in the literature of soft computing, ANFIS is the most popular one, which I'll be discussing tomorrow. Don't miss it. Okay. Okay, let me stop here today.